Yeah. So now, now I'm going to talk about. Maybe I should put. Yeah, just a moment. I will share the screen. Let me see with. Yeah, but if it's going to disconnect, I probably put another microphone. Okay. Does everybody online hear me?
Yeah, Yuri, we can hear you.
Yeah. Oh, wait. But I don't hear you. 1 second. Oh, okay. Can you say something? I just want to check that you
Yes.
hear.
Yes, we can
Okay.
hear.
Yeah. So I will. So I will do this through YouTube, and let me also put a video. So I will talk about example infrastructure. And you now have like opportunity to finish. You have now opportunity to finish installing, setting up. So before Alex talk about FIFO, and you can try different FIFO examples. Okay, so let me share my screen, and let's go to how this infrastructure look like on a GitHub. So if you go to GitHub, so let's go to okay. So, and let me make it larger. Make this thing smaller. Let me make this thing larger. Okay, yeah, this thing is too large. Okay, so this is a repository where we have all FPGA examples. So in this repository, users generally go into a directory called labs. So in labs, we have like a bunch of examples. They're like organized as like basics, graphics, music, microarchitecture, and so on. And inside it starts from like very, very simple examples. So inside it starts with example where you just put like AND gate. So you just put something like A equal key 0, B equal key 1, result is A XOR B, and you put RD. But every example has exactly the same header. So this header is called laptop, and it's a parameterizable header, and it has some default parameters like clock megahertz is 50 megahertz, so like number of keys is 4, number of switches, number of LEDs, number of digits on 7-segment display, screen width, color red, green, blue, and derived width of coordinates on the screen. Then we have a set of input-output ports. So we have clock, we have slow clock. So slow clock is artificially slow clock with frequency of 1 hertz, so 1 bit per second. And with this clock, we can see things like processor in action. Then we have like keys, and with like a parameter, we can have like different number of keys. So some boards have only 2 keys, other boards have 4 keys, 8 keys, 10 keys. There are boards with like more than 16 keys when we combine keys like buttons and switches. So same thing about like switches, LEDs. Then we have signals for 7-segment display, and we use here signals for dynamic display. So did you learn this static versus dynamic 7 signal? Huh? Huh? Yes, exactly. With the time, so here we're using time multiplexing, and we do it even with the board without time multiplexing, just by glue logic in the wrapper. So then we have inputs for the graphics. For the graphics, we have X coordinate and Y coordinate, and we user needs to create a function for that tells what is color of a pixel with the coordinates X and Y. Then we have a value for the microphone, like output for sound, because we have here microphones, and we have here sound output. Plus we have signals for UART, but UART is not completely implemented. And we have signals for general purpose I/O. So in a very simple example, users just do A equal key 0, B equal key 1, and so on. Now, so now, in addition to labs, so users mostly just go to labs and don't spend time like anywhere else. But in order to support this infrastructure, we have a directory called boards. And here we have a sub directory for all the different boards. So this is one important, and another is called scripts, and we have everything for the scripts. We also have a directory called peripherals, where we put the code for things like a microphone driver, like for like TM1638 board support module. And users generally don't look in here unless they want to add additional board or additional peripheral to this environment. So then in like miscellaneous is just some stuff. Then we have directory called docs with some writing up about how to set up, how to install, and so on. Then we have a directory where I put example for a book which I'm now writing together with professors from Purdue University. So I'm putting this as like illustrations for the textbook. And yeah, then we have bin, where we have RISC-V RAR simulator, which used together with examples used to like demonstrate simple RISC-V subset CPU. So now, but those are all not important. The most important is boards, labs, scripts. So now each lab inside has a set of scripts. So script is clean, simulate, synthesize, configure, run GUI for FPGA synthesis, choose another FPGA board. There are also scripts for synthesis for ASIC using OpenLane, but because I now recommend like everybody to try tiny tape out, this is not used much. For this, you need to put support for like OpenLane, OpenRoad locally, put Docker, and like it's like additional hassle. So like I don't support those scripts right now. So Now, text inside each script is exactly the same, because this is not actual script, this is a redirect. So actual scripts are located in a directory called script. And what script in example is doing, so this is a bash script. So how many of you know how to write scripts in bash? Yeah, so some like number, yeah. So this like useful skill. You can, but you can do same thing in like Python or like in other scripting languages. But with the Python, there is a problem with many incompatible versions. So for this reason, I was just using bash for this.
So every time you want to add a different vendor, add another support for the synthesis, it's you're gonna have to
And then you show how what is going, how we actually do this. Yeah. So now so what this bash script does, this bash script just get a current, get its own name, and then it goes up in the tree to search where is the location of script directory. Then it goes into script directory, finds the directory called steps, and find here script with its own name, but with source bash, like clean, find source bash here, simulate, find source bash here, synthesize, get source bash here, and so on and so on, right? So now, if you look inside, if you look, for example, inside clean, so what it does is first, like it runs setup, then it removes a directory called run. So when synthesis script run, it creates a temporary directory called run. So clean script just remove it. So now, if we run synthesis script, so let's go back to some like example. So, and you can see that the code inside every redirect script is exactly the same. So now, there is a directory which is called hackathon, and hackathon is a directory which has somewhat different examples. So this hackathon is used for people who are like either like high school students or people who don't know Verilog at all. So, and they need something simplified. So for those people, if you look to the hackathon top, this is simple to laptop, but you don't have parameters. You can see that everything here just uses hard numbers. Like if you have key, it's only like 8 keys. Because a hackathon is only for this specific board, for 10 nano 9K board. So, but lab can run on 46 different boards. So you can run it on Xilinx, you can run it on Altera, you can run it with Basis 3, and so on and so on. And how our scripts figure out that this is the board, they figure out by parsing code with this command. So bash script just look to this command, see name of this board, and just use name of this board from config. So now what happens if you go to script? So if you go to script, let's say like synthesize script. So what it does, it first runs setup script, which sets like different environment variables for like different tool chains, and then it checks that case FPGA tool chain is Quartus, Infinity, Gowin, Xilinx, Yosis, and then calls function synthesize for something. So basically, when you add support for microchip, you need to put here also microchip and synthesize for a microchip. Okay, then once this setup file, it puts some bunch of variables for where things are located, like in labs, in peripherals. Then it may do some Windows, Linux, or macOS specific things. Then it has functions for error warning and so on. So this is just a bunch of some utility functions, which are used by like other scripts, like platform specific workarounds. So if some toolchain has current bug, how to work around it. And it also maintains board select files. So when you choose board, it writes what board is chosen into a local file. So let's see this local file in here. So if you get where is our so like if you get here, so if you look to the files, you can see that there is a FPGA board selection. So this is a text file which puts a list of boards, but only one board is like uncommented. So when you select board by number, the board name is written in this file. So this is how you know what is the current board. Yeah, so basically it just changes the comment in the file. Yeah, that's it. So now, let's go back here. Yeah. So and like you see that it then it's set up a temporary directory. So if you go to our current file infrastructure, if you go to, let's say, like labs, like if you run something, so if we, let's say, do open an integrated terminal, and like as we run something here, like 03 synthesized. So when we run, you can see that it created directory called run. So it put all temporary files inside run. And if you go inside run, you can find all sort of information, including static timing analysis report, like error. So you get all the reports here as well as all the bit files here. So basically now, like in order to get rid of everything temporary, all you need to do is to delete directory run, and that's it. So you don't need to figure out what is temporary in your main code directory and what is not. So now, and also we create a project file inside run. So in Xilinx, all Xilinx files are copied into run. So now let's actually do this using both Xilinx and Gowin as examples. So for each, so if you go to script, so if you go to steps script, what time is it now? It's 2 o'clock. Well, okay, so we have time. Yeah. So this has so like if you go to Xilinx, so this has the following functions. First, wait, I want to just move this thing somewhere out of way. Yeah, so this has the following functions here. So first it checks that this is run from another script, and that not it's like somebody out of blue just do sources this file, because it doesn't want to be run by itself naked. Then you have a function Xilinx setup Vivado. And in this function, it's trying to figure out where Vivado is set up, where it is installed. So it also checks that Vivado has to be run either under Linux or under Windows, and Bash under Windows uses MCs or usually uses MCs. Bash for a Git Bash. And under WSR, it uses Linux GNU. So then it's trying to first guess that so then it's expected certain structure. So it expects that it's installed in Xilinx Vivado, and then it check the environment variable Xilinx Vivado is set. So if you set environment variable, it gets location of Xilinx installation from there. Like otherwise, it's saying then it checks whether installations they exist. So if it exists, it put into pass that this is where the thing is installed. Okay, let me quickly check that it's recorded. Yes, Lars and everybody. So can you hear me now or not?
Yes, we are able to hear you.
Yeah. Okay, good. Yeah. Like I'm just like checking that recording works, because this is like an important thing to have recorded. Yeah. So now next thing what happened, then if you don't define this variable, it looks whether Vivado command is executable, whether it's in the path, whether we can run it. So if you run it, we assume that we already can run it, so we don't need to set up any variables. Then it is trying to check whether there is the environment variable Xilinx home, and Xilinx home is somewhere where Vivado installation is located. So if such thing exists, then it put it as a parent variable and then figure out if it has multiple versions of Vivado, it takes the latest one. Because some people install multiple versions of Vivado, so this one chooses last one. Okay, so then it's trying to find Vivado and store in different locations. So for Linux and Windows, it's trying different things. So here, like, it checks whether it's installed like here and there, and then it's trying to find all versions in Vivado directory. Yeah, but this is actually a function which Xilinx setup Vivado. Okay, so for Linux, first it looks in a home, in like $home. Then if it cannot find it in $home, then so like if it's Windows, it looks into drive C, so /C. If it's Linux, it's trying to find in, I think, OPT. So let me see the place where it's looking for OPT. So here is like it's doing some checks and guesses. Yeah. So find dir, find OPT. Okay, where does it look for OPT?
Exactly.
Yeah. It also looks into tools. So let's see. One second. Yeah. So you see, it's this is upper Macintosh. I need to use this step. Okay. Yeah. So you see, So you see, like it's trying to find it in tools. It's trying to find it in OPT. So like it's So first it's trying to find it at home. First it's trying to find it at home. Then it's trying to find it in OPT. Then it's trying to find it in tools. Yeah, for like microchip, we just need to figure out where people usually install it. Yeah, look to default, and even if and some people like to install it in some other places, so we need to look for other. Like upper Macintosh, people download Vivado in downloads, and if you just like unzip it there, you just have it effectively installed inside downloads. In which case, I look for like downloads. So now, once you figure out where the thing is installed, we need to set up run directory. And in run, we need to create a project. So what do we do for project? We first copy there our TCL file for FPGA project synthesis and FPGA project configure from a directory called scripts FPGA. So, and this has Xilinx Vivado configure and Xilinx Vivado synthesize. So here is a TCL file for Xilinx, which for synthesis like do create project and put the all files here. So put so this is a TCL script. So and microchip may also use TCL for the same reason. So you can create similar script for a microchip, just using their examples. You get their examples and use their scripts as a basis for support, like in our infrastructure. And this TCL script run design, write checkpoint, do like power, then write Verilog. So everything in this TCL file. And then there is TCL file configure, which runs like open hardware, connect hardware server, and so on. So what we do in our script, which we discuss right now. So here's a set of things. So we first we copy those two files. Actually, we don't need to do anything here. Like everything is in Xilinx script. So we just copy it and that's it. Then how we run synthesis command. For synthesis command is called Vivado with switch mode batch, and then we get this script file which we copied, and then we put and then we parse whether we got error. Same thing for configure, we do Vivado mode batch configure. Very easy. So that's it. So you see, you have the 255 bash file and two TCL script, and you practically implement support for Xilinx toolchain. Yeah, with the Gowin, it's similar, but just a little bit more tricky. Because in Gowin, we need to actually create project file. And in Gowin, it has problems with passes for Windows and Linux. So with the Gowin, we do same thing. So we do Gowin. So we have function like Gowin finish setup, where you put passes for where everything is located. Then we try to find Gowin installation in different places, and we look for it in /Gowins in so where else? We look for capital Gowin and lowercase Gowin, and we are essentially looking for a file there called GWSH. So we are looking for this particular directory in different location. So we are trying to find executable which actually runs Gowin scripts. So, and in all scripts, if it doesn't run, find where this is found, it is asking you to set up environment variable so it can find using environment variable. So this is another. With like Altera, things get tricky because with Altera, some older boards need version of Quartus up to 13.1. And they are usually installed in a directory called Altera. And for newer versions, they are installed in directory called Intel FPGA. So for some boards, you need to look there. For some boards, you need to look there. And for some boards, you can look in both places because they are supported by old Quartus and new Quartus. So now for macOS, you have additional hassle. For macOS, at least previous version of Gowin for macOS, macOS complains that this is malware. So you had to put a special command with sudo to remove malware attribute, sudo xatter to remove it from quarantine. Because upper Macintosh with previous versions was just deleting it as a malware. So, but I think the new version doesn't do it, but I didn't try the latest version. So, like I just found, latest version. So we found this today. Yeah, but with so now second thing is when you set up. So when you set up, so you then you also with the Gowin, it's also trying to use under Linux program called OpenFPGA Loader. This is like open source a programmer, and you can use either this one or you can use Gowin one, which the Gowin puts together with the package. But the Gowin one didn't work well with previous versions. So we were putting by default, if OpenFPGA Loader is available, we use OpenFPGA Loader. But current version of Gowin works well with both OpenFPGA Loader and their proprietary things. So, but we still a little bit prefer OpenFPGA Loader. So then here it has call functions, try different directories, like try home, try PT, try tools, try home downloads, because people just downloads and just stays there. And for Windows, we were trying whether it's installed in drive C, drive D, drive E. Yeah, then what else we do with Gowin? Yeah, with the Gowin, we had to do workaround under macOS to put environment variables DYLD framework path, DYLD library path, and maybe new version is doing this differently. And also, this might be the reason why the newest version of Gowin, like under macOS, doesn't work well, because we put here LD library path for certain thing. Yeah, so then we have to do various little hacks to work around deficiencies of the tools. Yeah.
But on Windows, the installer first try, but on
yeah, no. So you had to do such workarounds here. Yeah. So now yeah, so okay, now we need to create project. So in order to create project, we had to collect all SystemVerilog files used in the project. So we have to collect current user files, files associated with the boards. So this is like our current source dir, then files from the board directory, files from peripheral, and files from labdir common, which have some common subblocks. So in a loop, we just go there, we get all these files, and we put them as add file. Yeah, here it would be better put not echo, but printf, but fine. Because initially this file was written not by me, but by two other people, and then like I edited here, but echo is still here. Yeah, so we put echo and create file called FPGA project tickle. So then we also need to create two other files for Gowin called FPGA project gprg. We actually create this file by combination of three files, by beginning FPGA project PRG, end of FPGA project, and then we insert some files inside. So here we form several text files in bash script. Yeah, and once we form it, synthesis is easy. So we just run a Gowin application with this tickle project file, and it runs everything. Yeah, we just created tickle project file in the run directory, and we put our original template plus we put all the necessary files for it. So we generated in this script. Yeah, that's it. Same thing should be done for like microchip. We just need to create tickle file, put all files, all settings, ship it into run, and run the command line tool. That's it. So now When we do configure Gowin, we check whether open FPGA loader is available, in which case we use open FPGA loader, otherwise we use a Gowin proprietary tool.
They just say that they have to use, can't find the latest version of migration. Make a
Yeah, you can do some warnings there, put like all kind of information. By the way, for Gowin, and here there are some settings for configure using proprietary with different options, and then configure using open FPGA loader with different options. So, but those are just a combination of some like hacks to put together command line for their tool and then to run their tool. That's it. So now if you look to, for instance, open source tool chain, which is like Yosys based tool chain. This Yosys based tool chain does something very similar, but it just uses like open, like also like forms approach. But this I think forms a make file actually. Yeah, so this forms a make file. Yeah, like this was done by a person who his name is Ruslan Zalata. So he just uses open source toolchain in principle. So he like doesn't want to use anything else. So now then you do configuration. Yeah, that's it. Similar thing for like Altera. We also form project here. So now if you go to board directory, yeah, so also when we do this, sometimes we need to tell to user if something doesn't work that he needs to put a rules file here to connect with the through like USB, because Linux requires rules files into USB directory. So we just put necessary files here. So here is some like yeah. So now this is about scripts. So now let's go to boards directory and see what we have in boards. So if you go to Xilinx, if you go to basis, so what you have in basis, you have here. So here is the most important part actually. So here you have XDC file. XDC file for Xilinx we got straight from Digiland. So this is vendor file. We are not trying to do like anything funny with it. Then we also get some tickle file which just tells to Vivado what type of board and chip, what type of chip we are using. And we also put our name for the board. And here is where main work is. So here is a file called board specific top.sv. So like so far, like everything else was to support a new tool chain, you need to change script, but to support a new board, you mostly need to change this file. So what this file does that you have board specific pins in XDC, like you have here you have board specific pins in XDC, like switch, button, like button C, button D. So you need to map all those buttons to our keys and switches. And same thing about like VGA ports and so on. And this board specific, it uses ports which are specific for our board from vendor examples, from like Xilinx, Altera, and so on examples. And you create, so it has this module port, and this has glue logic to instantiate laptop with appropriate connections. And also it passes to laptop parameters like clock megahertz, number of keys, number of switches, and so on. Yeah. So in this file, we like overwrite default parameters in laptop so that people work with the actual number of buttons, actual number of LED, actual frequency, and so on. So numbers in laptop are just like abstract numbers. And here is a specific numbers for this board. So this like basis 3 board has 100 megahertz clock. It has VGA port with pixel 25 megahertz clock. It has 5 keys, 16 switches, 16 LEDs, 8 digits, 7 segment display. It has 24 GPIO in like our IP mode connectors. VGA, we support screen with 640 by 480, and the color channel in VGA is 4-bit. So in basis, you have 4-bit. So then what we do here is we put our reset because this basis 3 doesn't have dedicated reset button. We use one of switches as a reset button, which is like leftmost switches. So this is switch -1. Then we put 7-segment display. We need to connect our port A, B, C, D, E, F, G into seg0, seg1, seg2, seg3, DP. So we just connect to names from the vendor examples. Then we put signals for graphics, and we need to use signal display on, because when you this signal from like VGA controller, so when you are like out of screen, it should make black color, otherwise it doesn't work on screen. So then you put the slow clock using a module called slow clock gen, and slow clock gen just uses counter to divide clock, but then after you use counter to put it to proper clock network inside of FPGA, you need on Xilinx to use pseudo module buff-G. And this pseudo module is different for each vendor. Like in Altera, it's called local. In Gowin, it's called just like in Xilinx buff-G. And this thing is located in peripherals. So if you go to peripherals, and this, or maybe in common. So let's see. Is it in peripheral or in common? So slow clock. Very slow clock. Jurassic socket. Or maybe this is in common. Okay, let's see. Yeah, so in labs, if you go to common, wait, where is slow clock? Slow clock gen. So 7-segment. No, this should be in peripherals. Slow. Yeah, here slow. Yeah, this is peripherals. So in slow clock gen, you have a counter which actually uses information about clock frequency, and then if you have Altera, you need to use module global. If you have Xilinx, you need to use buff-G. If you use simulation, you don't need to do anything. So for Gowin, I think you also need to use buff-G, but for some reason I didn't put it here. Anyway, so now if you go back to the boards, to bases. Yeah, so what you do after this, you instantiate laptop with appropriate connections. So you connect key to like button D, button U, button L, button C, button R on this board. Then you need to instantiate modules like VGA controller, something which converts our coordinate and maintains inside counters for the VGA. Then you also instantiate controller for microphone, which is connected to P mode connections in basis 3 and gives you just level of the microphone. And then you need to instantiate audio, where you have level of sound you need to output, and you connect it through P mode connector in basis 3. So if you look to this module, they are located in directory called peripherals. And you can see that for microphone, it, for example, uses a thing called I2S receiver. So this is a liter module with just like 88 lines of code, which maintains shift register. So it accepts bits from I2S interface one by one, forms level, and gives you level what is microphone level. And now you can recognize nodes by checking where level crosses 0. So when level crosses 0, you start counting. When it crosses 0 again, you stop counting. So now you know number of clock cycles for a period of sound. And then you can compute whether it's like node A, B, C, and so on. I see. Yeah, so practically for microchip, you need to put exactly the same things. If you but basis doesn't have this TM16. Can you show me the board? Let's see what it has. Okay, so what do we have on our microchip? First of all, we don't have buttons, so we need to connect this TM1638 connector, right? Huh?
8 switches on the top of it.
Yeah, so like it has switches, but they are not convenient to press. So it has couple of buttons here. So like as the user buttons. Okay, so you can use it, but we can extend more buttons here. So we need to connect this into GPIO. So this has also does it have connection to like HDMI, like is USB? Yes, this is this USB. So it doesn't have any like HDMI, right?
No, so
Okay.
USB-C.
Yeah, so we can actually use VGA, like is that little connector, you can use full VGA connector. Yeah, so we can just, what is this?
Yeah, I checked it earlier.
It's a MIPI connector. Yeah, we can just use a VGA connector using this pin. So
Do you have a diagram is made for the different boards for the connections, or only for this?
you can extract this all from files in board directory. Yeah, if you can make this, that would be great. Yeah, for all the different boards. Yeah, we also we want to improve like documentation all the time. Yeah, there are people like in different places. This was actually used in like around 30 different universities, most in places where I was traveling and making seminars. Yeah, so and people in like many places just created their own like diagrams and instructions, but some of those instructions cover specific boards, like board does with Altera Cyclone 4 is like well documented, but most of boards are not well documented. Yeah. So now. Yeah, so this is microphone. So now let's go to Gowin, to this 10 nano board, because this is better example, better connected to the thing. So with a Gowin, yeah, let's briefly look inside how VGA connector look like. So in a VGA. In a VGA, all you have is essentially two counters, which just form horizontal and vertical position, and you send H-sync and V-sync signal to VGA, and together with the colors for the pin, VGA get information what it should draw in this like place. So the code here is very simple. Similar thing like is an LCD. With this board, I actually need to read what other peripherals, because maybe it supports HDMI in some way, or so. Are you sure that it doesn't have anything else? No, oh, wait a second. They have some like a additional board, I think. So this has. Yeah, you can just use all this thing for like anything you want. So we can put like even like DVIs there and use it with HDMI interface. And DVI is similar to VGA, so we can put like HDMI connector in this way. Yeah. So now there is the module TM1638. It's for this interface module, which you can instantiate to just add additional keys and LEDs and 7-segment display keys. And this is how it's done in. This is how it is done in a 10 Nano 9K. So in 10 Nano 9K, you can see it's very similar. So what you have here is that you have like SDC. It's effectively TCL file to set timing constraints. Then you have TCL file to set options for the Gowin. Then you have CST. So CST is like equivalent of XDC in Xilinx. So you have a CST, and in this like CST, you have clock, key, you have LED. So you have like different pins associated with the numbers, and then like I use actually some pins not in a way they originally intended. For instance, I use pins for like small LCD as pins for like audio output, because we don't use small LCD, so I use it for different purpose. Yeah, but I propagate these names to the board specific wrapper with their original vendor names. You see? So now if you look, so then there is some top of project file, which is in such like XML format. So I get this top, and I this was code for this was created not by me. It was by another person, but he generated here a bunch of Verilog files, and then he put like ending of this file using this file. So we combine 3 files together to form a project file. Then we also need to put JSON file with setting options, and also need to put something in the middle. Yeah, so we have here connection, which is by the way obsolete. This should be replaced. Yeah, but the main thing is the board specific top. So here now, like, watch it very carefully, because this is what you probably need to do with the microchip board. So here we do have on 10 Nano 2 user buttons and 6 LCD, but we want to connect them instead to TM1638 interface module. So we put here that we have the 2 keys, no switches, 6 LEDs, no digits, 6 pins for GPIO, and we have 27 megahertz clock. And then what we do is we create we like repurpose small LCD signals for GPIO. Then we put constants called WTM lab key. So those are constants here. So how many keys, LEDs, and digits we have on this TM1638 interface module. Okay. So then when we do a lab top, so here we do some tricks to do a reset for this thing, because TM1638, initially we were using a button on this TM1638 like as a reset, but we cannot use it as a global reset because TM1638 itself needs a reset. Okay, so we had to do a fake power on, power up reset by using FPGA specific trick, like FPGA toolchain, unlike ASIC, allowed to like initialize logic variables. Like ASIC doesn't allow it. In ASIC you need to use reset, but here you can just put that something is equal 0, and then on reset set it to 1. Then this is like on power up. So so here we fake reset by a module called imitate reset on power up. So if you go to peripherals, you can find this module imitate reset on power up. So in this module, you simply put reset R is equal 1, reset is equal reset up, and on first clock edge, you put it to 0. That's it. So then then we put some like glue code for like swapping bits because this board and our abstract board uses different order bits. Then we instantiate the slow clock gen here. Then we instantiate either hackathon top or laptop, whether we have hackathon or laptop. So with a laptop, so what we do here is that we put a WLAP key, and like our WLAP key, if you go back, you can see that our WLAP key. So here we have wire lab key, and this lab key, depending on defines, is connected to either so lab key to either key from TM1638 or real thing on the board. So if we instantiate TM1638, because we have configuration where use this board without TM1638. But when we use it together with this connector, we need to connect it to wires for TM1638. So yeah, so we have here like a bunch of like multiplexing variables like with TM1638 and so on. So then yeah, so we put here a key, lab switch. Then we put here X and Y, and we like output our color to larger CD RGB directly. Then we have microphone and same thing. So TM1638 board controller we instantiate. Then we instantiate PLL necessary for this thing. This thing needs PLL. And then we instantiate controller for the display, which I got from a Gowin directly from their example. So we are using vendor example to create code in like our example. Then same thing for the microphone and same thing for the sound output, and that's it. Yeah. So now is there microchip examples available somewhere? So what is the name of this board again? Okay, Polar Fire SOC Discovery GitHub. All right, reference design. Here is where to get all the necessary information. So what you do is, first you look to constraints file. Yeah, so this has like a lot of, okay, so HDR, what is that? Can you do something with it?
It just turns off after 4 hours.
Oh, okay.
It should turn on.
Ah, okay. Yeah, so you continue in just a moment. Yeah, let's check. Yes, yes, Lasse, can you still hear? So does microphone works? Yeah, maybe she's not here.
Yes. We
yeah,
can
okay,
hear
good.
you, but the screen share just now stopped when
Yeah,
you're.
screen view put it back now. Yeah. Okay,
Okay.
so now yes. Okay, let me get water. Run the thing.
Which source is that? It should be just computer. It's still not showing up. No, just like take it out and replay it.
Okay. All right. Oh, by the way, I was thinking, what if? I know, let's not experiment with a microphone right now. Okay, so now let's put back screen. Okay, so yeah, so we are sort of look to this code. So now let's look to what's available in a microchip. So here, okay, so just a second. To check whether. Okay. Yes, Lasse, can you say again whether you can hear, because there was some like interruption of microphone.
Yes, we can hear and also see.
Okay, good. Okay, good. So now, so so let's see. So they have script support additional configurations. So what you want to find? You want to find a place where they define their settings. Discovery kit. Huh? Yeah. Okay. So they have something like PDC. You see, they have a set IO port name. This is like what we are looking for. So you need to get this like, so their file is called PDC. So you just need to like extract information from here. So this is for UART. Okay, so well, this is demo for somebody. Oh, this is FAR demo for basic constraints. Okay, so you have, oh, they have IO bank settings. So they have reference clock, UART, RxTX. So yeah, do they have anything else? Switch IP name. Okay. So what about? Oh yeah, this is this is there for seven segment display. Huh. They using SPI protocol. Ah, okay. So they using SPI. Yes. So maybe this is for like external connector. So for UART, let's actually see like other examples. Polar fire. Yeah, at some moment actually look to Polar Fire SoC Linux example. Okay, so yeah, GPIO. But this is all software examples. So where is their hardware constraints? Polar Fire. This is embedded. Bootloaders. FPGA build system. This is IC call. Yeah, reference design. Yeah, I would think this is the same reference design we look at. Yeah, so we need to like extract such information from here, essentially. So we need to run some examples and extract information from here. Just see like all their. I got some their documentation. And like I think that I saw that they have all the necessary. We need to first connect TM1638 there, or just first make port with just one LED, one button, just to see that script works. And then to connect TM1638, and we have complete support. Yeah. So Polar Fire SoC. Polar Fire SoC. So let's see what other resources available. This is what we need. Libero reference design. Yeah, this is what we need. This video kit reference design. Anyway, so you see, you have scripts here. So you have scripts here. So you just look to. So this is how to create project. So you simply go here. You get there like documentation, and you write equivalent of such scripts, and then they have some like Python file to which creates project and so on, which is the same thing as like bash script. So it creates some project and then runs something. Yeah, so you can just search for this existing information and search for their documentation and figure it out from here. So this is kind of useful thing to do. Yeah. Now reference design. Yeah. Video kit reference. Yeah. So same thing is here. So this is just. Yeah, so just like scripting documentation. So another thing, if you are interested, I'm looking for somebody who can help in supporting like additional this high-end Gowin boards, like that board with 100. I mean that board for 130K with high high-speed receivers, like I have already example. But a board, a smaller board, which costs like under $100, I don't have support. So like if you want, I can leave you that board and you can try to implement the support. So this is like one thing. So one thing is this board or like on AliExpress. So if you go to Gowin, so this board I'm talking about is, maybe I got it not from AliExpress, but from somewhere else. Yes, it doesn't matter. It's Gowin 60K. Gowin 60. 10 Gowin boards. Yeah, there is a third-party boards. So this is like SciPid Wiki, and this has 10 mega. Yeah, this has 10 mega board. This is 10 mega 60. No, this is a different board. Yes, anyway, like I will just leave you that board and another board. If you like, I'm looking for somebody who like implements some like practical and elegant support, is like small board with Arctic 6, which is breadboardable. So yeah, so this is like also I'm looking for somebody who put everything. So microphone, sound output. So like if you implement those 3 boards with Arctic 7, with Gowin and with microchip, you will have a pretty good idea how to do this for like any like other board. So yeah, this is like useful help because I got this high-end Gowin boards recently. And like also with like Arctic 7, that board, several people were like attempting to do this, but they didn't do it to the end properly. So I want to do this to the end. But one thing with the Arctic 7 board, this TM1638, it is asking, like it's saying that its power VCC is 5 volt. But actually, you shouldn't use 5 volt, because if you use 5 volt, it gives 5 volt input pins. You need to use a 3 and 3 volt. It works perfectly with 3 and 3 volt, because with 5 pins, if they go back to Arctic 7, they can burn it up. Yeah, and the board I'm talking about is called Digilant S mod. I think it's called S mod 7. Let's see. Yeah, I'm talking about this one, A7. This one, A7. So have you see this board? This has the same. This is a Spartan, and there is also Arctics. This is, has the same FPGA as like base 3 board or similar, but so here's a base 3. So which FPGA it has? It has, I think it's like also Arctic 735. Yeah, but and here is breadboardable. Yeah, this one CMOD A735 T. Yeah, so this one is probably easiest for you to do right away. And you can also connect TM1638 to it as well. So once you do this, and once you do Gowin boards, and like in parallel with the microchips, then you should be able to do everything. So what you can do is that you can just fork a repository, either my personal or from a Verilog Meetup, and modify your forks, and I will review and you do pull request. And then we discuss over Zoom all the technical problems. Yeah. Okay. Having said that, so now let's Alex teach everybody what FIFO is and talk about our AI challenges. Yeah, but I think for you, let's connect your computer here, and you put into Zoom. Right? And then you use your microphone, so this would work better. So let me maybe shut down my computer or simply turn it. Let's just disconnect it. Okay, put everything to yours. So you just need this thing. And wait. So this is. I need to move. I need to move to my telephone. Okay, first of all, let's stop recording and start it again. Oh, Wait, I need to connect this back because I need to stop recording in here. Sorry. How to connect this thing back? Disconnected it. Can you help to connect it back? So let me just get control on the telephone. Okay. I don't see chat. Yeah, okay. So now let's go back here. One moment. Oh, yeah, I will be organizing here. Okay. Okay, so now I'm organizer, so I will stop recording.